Hello, everybody. My name is Alexander Kamkin. I'm a leading researcher from Institute of System Programming of the Russian Academy of Sciences. My talk is about online test program generator for microprocessors. So online means that test programs are generated on the fly, and test program generator is co-executed with design under test, and it works inside design under test. CPU execute generator, which generates test programs and execute them on the same CPU. So our approach based on MicroTESK, it's a specification-based framework I told 2 years ago. Its framework automates development of test program generators for microprocessors. So we have specified basic integer subsets and some standard extensions and are developed offline test program generator for RISC-V microprocessors. And today I'm going to tell you about online test program generation. So let me recall how MicroTESK works. So it uses NML specifications, which isocentric specifications. Language was developed at Technical University of Berlin in the early 90s. Specifications are translated into the processor model, which quite complicated object. It consists of several layers, including metadata that represents syntactic information about instructions, simulator, which is built-in interpreter of microprocessor instructions, and coverage model, which represent instruction execution path in form of constraints. Model is shared among different engines. One of them is test program generator. It analyzes the model and produce test programs, which are assembly code with compilable code with linker script. There are also some other engines, for example, binary code analyzer. It takes binary code, reconstruct control flow graph, and annotate basic blocks with SMT-lib formula. And there are also so-called tool builders that construct other representation of instruction set architecture. Reference simulators in some formal specifications to be used in for formal verification. To be sure that specifications are correct, we use the following debug loop. Generated test programs are executed on reference simulator, Spike or Camel. In a sense, results are compared with built-in simulator. So in having this debug loop makes us confident that we use valid specifications. And again, we use specifications not only for test program generation, we also use them for formal verification, for binary code analysis, and so on. So here is how NML specifications look like. We have constants, we have data types, bit vectors interpreted as signed or unsigned integers or floating point numbers. We have registers and memory. We have so-called addressing modes, encapsulating function for accessing those registers and memory, and also operations, the main part. Each operation is described with the help of three attributes: assembly syntax, binary encoding, and semantics, action. The language also supports and or rules that makes it possible to compose complex operations from simpler ones. Unfortunately, language is not powerful enough to specify a memory management unit, and for this reason we have developed MMUSL, some extension of NML language. It allows us to specify addresses, physical addresses, virtual addresses, some intermediate addresses, and address spaces that maps virtual addresses to physical addresses, some buffers like TLB, cache memory, and so on. So, and of course, overall memory access logic. And having these specifications, memory specifications, allow us to generate memory-related test programs. So this slide shows some statistics on RISC-V specifications in NML. We have specified basic subsets, excluding 128-bit arithmetic, and some standard extensions like multiplication and division, atomic operations, single and double floating point operations, compressed instructions, and so on. We also specified address translation mechanism. So now we are able to generate rather complicated test programs, including memory related stuff and so on. And we have also specified partially vector instructions, but this work is in progress. Okay, this is a basic scheme of offline testing. Test programs are executed on design under test, which is RTL model, FPGA, or integrated circuit. The same test programs are executed on reference simulator, SPI, Camel, and so on. The results are execution traces, sequences of events, or signatures, some regions in memory. Results are compared with comparator, and its output is so-called verdict, either positive, true, meaning that no bug is detected, or false, meaning that there is a bug and we need to determine which of the component designed at the test or simulator is incorrect. So the main question is what's inside that box on the left. So in other words, how to generate test programs, how to automate test program generation. And we use a so-called model-based or specification-based approach. The idea is to separate architecture-dependent knowledge from architecture-agnostic generation core. The idea is not new. It was originally implemented in Genesis Pro in IBM Research. So there are two inputs. Specifications in NML and MMUSL are translated to processor model. Again, processor model consists of metadata, simulator, and coverage model. Another input is test template or a set of test templates. Test template is a description of verification scenario in a Ruby-based domain-specific language, DSL. Generation core implements architecture-independent test generation techniques to compose complex sequences of instructions, to generate test data using randomization and constraint solving, and produce compilable assembly code to be used for testing. This is the basic scheme. Of course, we have more. We would like to automate this processor deeply, and we develop a special component called AutoGAN that analyze model and produce architecture validation suite automatically. It's not a complete set of tests, so some additional tests are required for high quality verification, but it's a kind of push button technology that automates some typical verification tasks in a systematic manner. And this is how test template looks like. It's a Ruby class. It describes prologue and epilogue not shown here, and a set of test actions. Test actions are described in assembly-like syntax. We can also use Ruby constructs such as conditional and loop statements to control instruction stream generation. We can also use some special constructs like block and situations. Block, for example, is used to compose complex instruction sequences from simpler ones, to combine them in a sense and merge them. Situation is a reference to coverage model. It's used to direct test program generation to some particular corner cases. This particular test template describes Cartesian product of two sets, each consisting of two instructions. So there are 4 test cases, and one of them is shown on the right. So you can see stimulus consisting of AND and exclusive OR instruction, and initialization code that puts generated test data into the registers. Yes, and by the way, MicroTESK offline is open source. It's distributed under Apache license version 2, so you can download and use it for free. Okay, and here is difference between offline test program generation and online test program generation. So again, offline test program generator is a standalone software. It generates test programs ahead of time. So millions lines of code in assembly language. Online test program generator is executed inside design under test and generates test programs just in time. It generates test programs dynamically on the fly. And test programs are used immediately. So it's binary code. The generator transfers control to that binary code and returns it back. So that's the idea. Let's consider the main requirements to online TPG, online test program generator. There are three of them: autonomy, performance, and robustness. Test program generators should be able to produce a variety of tests from a single test template, and it should be able to check test results automatically. And it should be emphasized that we have no execution traces and reference signatures, so we should do it automatically. Testing is performed at really high frequency, so simple techniques are preferred. We need to load design under test. So we can use some brute force techniques, some randomization, mutation, but no constraint solving. Yes, and robustness. Test program generators should not lose control, and there should be possibilities to save and restore the generator state. So that are the main requirements. Let's look at online TPG architecture in more detail. So there are two main parts, a residential part and an external part. Generator produce test programs. You can see two of them. The main test shown as green, and a mutant, a result of basic test transformation. Why do we need two tests? It refers to how we check test results. So we compare signatures of the main test and its mutant, and so we perform equivalent transformation of the base test. For example, we can insert some NOPS instruction between other instructions to avoid pipeline hazards. We can also use more complicated transformations, such as in QED, quick error detection. Okay, the allocator allocates test images in memory. One important remark, the generator also produces metadata that describes where to allocate test images, how to get, where to get signatures, and so on. So basing on that information, the allocator allocates test images in memory, and then executor transfers control to tests and returns back, of course. Test oracle obtains signatures, compare them, and return a verdict to the control unit that communicates with the external part. A control console takes input data from user, some comments and parameters, and provide output data, some statistics, test coverage, failures. It can also implement automatic or human-in-the-loop feedback to the generator. Okay, so if MicroTESK offline generates test programs, then MicroTESK online generates generator of test programs. So that's the main difference. And there are two techniques available: template-based generation and automatic-based generation. This is exactly the same test template that was shown earlier. Cartesian product of two sets consisting two instructions each. And on the right, you can see the generator. The generator is a C program that generates test programs according to the test template. It combines instructions, generate test data, allocate registers, and so on. This is a simplified view. It's not real code used just to illustrate the main idea. Okay, so the main features of Olline test program generator. So it implements some simple test generation techniques like combinatorial brute force generation, randomization, but no constraint solving. It can use pre-calculated signatures to evaluate test results, but usually it's based on equivalent transformation. So we have the basic test and we have a mutant, and then we compare their results. Let me conclude with future work directions. We are going to specify more subsets, more basic subsets, and more standard extensions, including, first of all, vector instructions. Speaking about Olline test program generation, we are thinking on error localization and diagnostics, because it's really so if something went wrong, it's really difficult to understand what exactly is exactly happened. So we need to provide some useful information to test to designers. It's a huge problem. Another issue is test coverage tracking. So high speed of testing reduces our abilities, reduce controllability and observability, and how to measure test quality, how to measure test completeness. Okay, another direction, it's a different story, it's compiler testing. So we are working on model-based test generation. So we are going to model compiler transformation and generate test programs in a systematic manner. And to check compiler results, we suggest using binary code equivalence checking. I mean, checking optimized code against non-optimized code, JIT compiled native code against original virtual machine code. Okay, so here are our contacts, website where you can find more information about MicroTESK. Again, MicroTESK offline is open source. It's distributed under Apache license. You can download it, use it for free. MicroTESK online is under development. It's not available yet, unfortunately. So thank you for your attention.